Today's our last tutorial on optics, and then next week we'll start on radiation, and we'll have 2 weeks of radiation. Okay. So today we're going to go over some more lens stuff, and just pretty much continue on from what we did yesterday, just a bit more harder questions. So our first question we have, we're told that the typical distance between the lens and the retina in the human eye is 2 centimeters. So the human eye, at the front of the eye you have the lens, and at the back of the eye you have the retina. So the image is going to form on the retina here. So the distance between the lens and the retina where the image forms, that's going to be your DI, so your distance to the image. So that's 0.02 meters. Okay, so that's what that's telling us. And it's always going to be a real image because it has to form on the screen, right? So the retina is acting as a screen, so it's going to be a real image, which means that the DI will be positive. So DI is equal to 0.02. Now, this person has a near point at 5 centimeters. So the near point is the point, the nearest point at which you can focus on something. So anything closer than 5 centimeters for this person would be blurry. Okay, and the far point, so the furthest point at which they can focus on, is infinity. So that's normal for most people, is their far point will be at infinity. So we want to find out the range of accommodation for this person's lens in diopters. So diopters is the unit of power for lenses, and what the range of accommodation refers to is the change in power between the near point and the far point. So you're going to have to calculate the power for the far point and also the power at the near point. Okay, so the power of a lens is equal to dO to the negative 1 plus dI to the negative 1. So when we have the I, dO will be the near point. Or this will be the far point, and so the object will be at an infinite distance, and the image will be forming on the retina, which is 0.02 meters away. So that's so 1 divided by infinity is just 0, and this is 50. So our power at our far point is 50 diopters. Now we'll do the same for our near point. So dO negative 1 plus dI to the negative 1. At our near point is 5 centimeters, so 0.05 to the negative 1 plus our dI, which is 0.02 to the negative 1. So that will give you 70 diopters. Okay. So the difference in power between the near point and the far point is 20 diopters. So that's going to be a range of accommodation. Okay. Now, our second one, we have a myopic patient. So if they're myopic, are they nearsighted or farsighted?
Near.
Yep, so they're nearsighted, and that means their lens is too powerful. Okay, so this person's far point is 5 centimeters, which means that anything further than 5 centimeters is blurry for them. So you can imagine that would be very uncomfortable. Alright, so we want to know how much, since the lens is too powerful, we want to know how much we have to reduce it by in order to have a normal far point power of 50 diopters. So you're going to calculate the current power. So power is equal to DO to the negative 1, DI to the negative 1. And that's going to be, so the DO will be the far point, which is 0.05. 1 plus the DI, so that's going to be the lens to retina distance, 0.02. And that will be your 70 diopters. So 70 diopters, it should be 50. So they'll have to reduce it by 20 diopters.
So does it matter which way you put it around?
Whether you do DI first or DO first.
Yeah.
It doesn't matter. Yeah. You can do DI plus DO or either way.
But it doesn't matter for when you're like doing the rearrangements either.
No, it doesn't matter.
Okay.
Yeah.
Oh my god, I'm so stupid.
Don't say that. No.
Like, so that's going to be on video now for everyone
I'm like
you cut
behind
it
it.
out. Why?
That's right, everyone can
So number 4, your patient has a near point located 70 centimeters from his eyes. You prescribe contact lenses, which allow him to read a book held 25 centimeters from his eyes. Assuming the patient's lens to retina distance is 2 centimeters, what's the power of the contact lens? So now we have 2 lenses. So we have the lens in our eye. So this is the eye. And you have the lens at the front of the eye. And you also have the lens which is in front of the eye. Right? The contact lenses. So when this is the case, when you have glasses or contact lenses, now the far point or near point becomes DI because the contact lenses or the glasses are going to create a virtual image for the real eye to look at. Okay? So for this person, the near point is at 70 centimeters from his eyes, right? So anything closer than 70 centimeters is going to be blurry for him. So if he wants to read a book which is held 25 centimeters from his eyes, the glasses have to create an image which is actually 70 centimeters away. And then so then your eyes are going to see the image created by the glasses, which is 70 centimeters away at his near point. Okay, so his DI will be the near point. So DI is equal to, and because it's on the same side as the object, right, it's going to be a virtual image. So it's going to be negative 0.7 meters, and so the actual book is the object, so that's 25 centimeters from his eyes, which is where his contact lens is also located. That's 0.25 meters. Okay. So our power would have to be dO to the negative 1 plus dI to the negative 1, which is 0.25 to the negative 1 plus negative 0.7 to the negative 1. Okay. Or you could just take the plus out, doesn't matter. That will give you 2.7 diopters. Okay.
So you didn't need the retina distance at all?
No, you don't need the lens to retina distance in this case. There's another way you can do it. You can also calculate the power of his eyes with a near point of 70, and then you could calculate what the power would need to be. So if you calculated the power of his eye, so the power of his eye, obviously it's going to be not powerful enough because he's farsighted. So he's going to have his near point is 70, which is dO, so 0.7 to negative 1 plus 0.02 to negative 1, But anyway, I'll just do it like this. That's easier.
So with a contact lens, I don't know. Oh, I was just, don't worry, I think we're going to cover it in the next question.
Yeah. So that one's simpler because there's no distance between the, there's no distance between,
Between the contact lens and the eye.
yeah,
Okay, so that's why you don't need to add.
yeah, so that's why you don't need to do any further calculations, but in our next one, we're going to have a distance between the eye. So the eye is here, right? You have your lens, and then your glass is actually going to be located 1.5 centimeters in front of the eyes. So you have, this is your, that's a bit off target. So you have, this is 1.5 centimeters. I should write in meters actually. So that will be 0.015 meters. So that's 1.5 centimeters, right? And then, so the object will be located, the book will be 25 centimeters from her eyes, right? So that's, so it's 25 centimeters, 0.25 meters from her eyes. Now, we want to calculate the power of her lens on the glasses, so we need the DO, that needs to be from her glasses, which is going to be 1.5 centimeters less. So that's going to be 25 centimeters minus 1.5 centimeters. So the DO will be equal to 0.235 or 23.5 centimeters. Right, now the image has to be formed at her near point, which is 50 centimeters from her eyes. So the image has to be here. So it's going to be a virtual image, which is why it's dotted. So image, so it's the book. And so again, that's going to be 50 centimeters, so 0.5 meters from her eyes, but the DI should be from the glasses. So DI is equal to, it's a virtual image on the same side as the object, so it's going to be negative 0.485 meters. Okay. So we have DO and DI, now we can calculate the power. So power is equal to DO to the negative 1 plus DI to the negative 1. So DO is 0.235 plus negative 0.485. So that will give you 2.19 diopters. Okay? The next one's pretty similar. So we've got, now this time we've been told the power of the glasses, so it's 2.5 diopters. When wearing these glasses, she can read a book held as close as 25 centimeters to her eyes. What's the nearest to her eyes that she could read the book without wearing the glasses? So we want to find out what her near point would be without the glasses. And so the glasses will be producing the image at her near point. So you want to find out what her what the DI of the glasses is going to be. So we want to find out the DI of the glasses, and that will tell us what her actual near point is. So again, we're going to have our eye, our lenses, and the lens in front of the eye, our glasses. Okay, so this is 1.5 centimeters, 0.015 meters. Now, we know that the book is 25 centimeters from her eyes, so that's 0.25 meters, but we want the distance from her glasses, so that's DO. DO will be equal to 0.235 meters. Right? And we want to find out where this image will be located. So DI is equal to P minus DO to the negative 1, and all of that to the negative 1. Okay. So our power is 2.5 minus our DO, which is 0.235 to the negative 1, to the negative 1. And that will give you negative 0.57 meters. Okay, so the negative tells us that it's a virtual image, and if it's a virtual image, it's on the same side as the object, so it's going to be 57 centimeters on the same side as the object, so it's going to be, oh sorry, this should be from the glasses, so this is the DI from the glasses. So it's going to be about here, so our image would be forming this is our image. Okay, so that's 57 centimeters from 57 centimeters from the glasses, but we want the near point of our eyes, so that's another 1.5 centimeters, right? So the total distance from her eyes to her near point is going to be 58.5 centimeters, right?
When you saw this question, like, obviously you knew straight away what to do, but how do you break it apart to sort of understand how to get that you need to find the distance to the image, which is wearing glasses and that will be the same thing? Do you just need to appreciate
I struggled
that?
a lot. I struggled a lot too, like when I was studying. Yeah,
Yeah.
I'd like spend hours on like a single question.
Same.
Yeah, and so like, I mean, I've been doing this for like 3 years now, so.
Yeah. So do you just need to appreciate, to get this question, the fact that glasses will create a virtual image at your eye's natural near point, and that's how glasses work? I mean,
Yeah, that's how glasses work, yeah.
Okay,
And they are the natural near point.
right. And that's always the case.
Yeah, that's how it's working, yeah.
Okay.
Yeah.
What was the answer to that? 58.4.
Yeah, so the distance from, this is where the glasses are creating the image, so that's where her actual near point would be. Okay, so that is pretty hard, it is a hard one. And like, don't be too worried if you don't get it, because that's probably going to be, that's actually like the hardest one there is. Number 7, we have a single slit pattern formed by light passing through a narrow slit, which is 20 micrometers wide. If the central maximum has a width of 120 millimeters on a screen placed 2 meters from the slit, what is the wavelength of the light? So we have our slit here, and we have our screen. So we have light coming through, and when it comes through the slit, it's going to diffract. Okay, and so you will create a diffraction pattern. The diffraction pattern will be like this. Okay, so that's our single slit diffraction pattern. Okay, and so this here, this part here from the first minimum on each side. So this is the minimum. This is the central maximum. The peaks are the maximums, and the troughs are the minimums. Okay, so for single slit, the distance is to the minimums. Whereas for double slit, the distance is to the maximums, okay? Now, it's usually just going to be for single slits that you need to know. Yep.
With the look the same, the diagram, like the big page in the middle for a double slit.
Yeah, it's pretty similar, except that for double slit, this central maximum is not as pronounced, and it's it's like more evened out. Yeah. But for single slit, it's like a huge central peak and then really small. Yeah.
Wait, so if that's projected on the wall, then the big peak is like, does that mean like bright light?
It just means bright. Yeah. It's
or
not,
like real like thick.
Yeah, like real bright.
Okay.
So it'll just show up as like a real bright spot.
Is it larger than the other maximum?
Yeah. So it'll be like a large diameter, and then the other ones that are going outwards would be.
Oh, yeah. Okay, yeah.
It's like that thing you showed us with the red line.
Yes, yeah, I remember now. Sorry, I was visualizing the wrong thing. Thanks.
Yeah. Okay. So this is just showing the intensity of the light
Yeah.
at this points,
Yeah.
at these points. Okay. So the width of the central maximum is this here. So from here to here is the width of our central maximum, which is 120 millimeters. Okay. So what that means is, so when we use the letter y, so you have this equation for single slit. Y is equal to m times the wavelength times L over the diameter of the slit. Okay. So the diameter of the slit here is D. Okay, and if you want to find y to the first minimum, then m is equal to 1, and if you want to find y, the distance to the second minimum is going to be 2, and if you want to find the distance to the third minimum, m will be 3. Okay. Now we want to find out. We can just say that m is equal to 1, so that y will be just half of this distance because it's from the center. So it's going to be, this here will be 60 millimeters. Okay, and that's our y value when n is equal to 1. Okay, so m is equal to 1. Sorry, we need to rearrange this first for wavelength, which is what we want. So wavelength is equal to y times d over m times L. So y is going to be 60 times 10 to the negative 3 meters. Right, so that has to be meters. And the slit width is 20 micrometers, so 20 times 10 to the negative 6 over m, which is 1, times the length from the screen, which is 2 meters. And that will give you 6 times 10 to the negative 7 meters. And if you want to turn that into nanometers, you're going to divide it by that prefix, which is nano, which is 10 to the negative 9. And that will give you 600 nanometers.
Sorry, what was y defined as? What did you find?
So y is the distance from your central maximum,
Yeah.
the center, to
M.
whatever minimum you want.
Oh.
Yeah, so if you say m is equal to 1, then y will be the distance to the first minimum.
From the central maximum.
Yeah, from here, from the very center.
So it's the minimum.
Yeah.
Yeah.
Yeah, and then if you say m is equal to 2, so if you said m is 2, then that's distance from here to here.
Yeah.
And that's just going to be twice the distance.
Yeah.
And this will be 3 times the distance, and 4 times the distance.
But it will still give you the same way. Oh, I'm confused. Because isn't the wavelength of the light the same?
Yep, the wavelength of the light is the same. So what they told us is the width of the central maximum in this question. So they said the central maximum has a width of 120 millimeters,
Yeah.
right? So that's this.
Yeah.
So you could have just said that y, if you wanted to say use this value, then you
Yeah.
could have said y is equal to 120 millimeters and said
m
that.
is equal to 2.
Yeah, yeah. So you could have done that as well.
Oh my gosh, okay. Of course, because y doubles. Yeah.
Yeah.
Okay, yeah. Sorry.
Okay. Now, our next one, we want to find out the width of the slit. So that's D. So D will be equal to, so D is equal to m times wavelength times length over y. Okay, so they said the central diffraction maximum must be 10 centimeters wide. Okay, so if we want to just have the distance to one minimum, that's going to be 5 centimeters. So let's say that the first minimum, so m is equal to 1. 1 times our wavelength, which is 633 nanometers, times 10 to the negative 9, times our length, which is 2 meters, over our y value, so that's the distance from the center to the first minima, which is 5 centimeters, so 0.05. So that will be 2.5 times 10 to the negative 5 meters, and you want to turn that into micrometers, so divide by 10 to the negative 6, and that will be 25 micrometers. Alright. So one more on single slit. So this time we want to know the distance from the center to the second minimum. Okay, so that means that m will be equal to 2. Okay, so we want to find the distance from the central maximum, so y is equal to m wavelength times L over D. M is going to be 2 times wavelength, which is 633 nanometers, so 10 to the negative 9, times our length, which is 1, over our slit width, which is 10 micrometers, so 10 times 10 to the negative 6. And that would be 0.127 meters. So that's 12.7 centimeters. Okay? Right, now we'll move on to circular apertures.
She's my friend.
So the moon is 384,000 kilometers from the Earth. A student is looking at the moon. Her pupils have a diameter of 4 millimeters. Okay, so the pupils are here. So the pupils are acting as a circular aperture, and this diameter here, so that's D. D is equal to 4 times 10 to the negative 3 meters. Okay, and so the moon is 384,000 kilometers away, so that's here. Alright. So that's going to be your x value. So x is equal to 384,000 times 10 to the 3 meters. Or you could just say 384 times 10 to the 6 meters as well. Okay, so you want to find out the smallest object on the moon that she could resolve. So that means that if there were two objects, so basically what you can think of it like is saying that if there were two objects, what's the least distance that two objects could be far apart, and she could still tell them apart. Okay, so we're looking for this distance here, so that's the y value, so y is equal to question mark. Okay. And you're going to have your string at the back here, so that's a retina. Okay, so when the light goes through her aperture, it's going to diffract. Okay. So it's going to spread out like this. And okay, so here they're not overlapping, so you'd just be able to resolve these. If they were any close together, this angle would become smaller, right? If they were any close together, this angle would become smaller and they would probably overlap, and you wouldn't be able to tell, you wouldn't be able to resolve the object. Okay, so what we're after is the y value. So the equation is y over x is equal to 1.22 times the wavelength over the diameter. Okay, so we want to have y on its own, so so y is equal to 1.22 times the wavelength, and then we're just going to move this up here, times x over d, and that's 1.22 times the wavelength, which is 550 times 10 to the negative 9, times our x value, which is 384, times 10 to the 6, and that's over the diameter, which is 4 times 10 to the negative 3. Okay, and that will give you 64,416 meters. these two objects have to be 64,000 meters apart or 64 kilometers apart in order
Is that true?
well, yeah, theoretically,
Oh my gosh.
yeah.
Wow.
But I think that's just like theoretical, like if it's just limited by diffraction.
Right.
But I think as the light comes through the atmosphere, it also gets diffracted by the atmosphere.
True.
But I don't know. Yeah. Try looking at the moon on a clear night. But you can see like craters and stuff on the moon.
And apparently they're really far apart, and like, but we see them, but they're actually really far apart.
Then they look.
Yeah.
Oh yeah. I don't know. I've never.
Measured them.
Yeah.
I think you missed a number.
Did I?
1, 2, 3.
Oh,
1, 2, 4.
1, 2, 4, and 2, 8. So it's still 12, it's just.
Oh right.
Oh, not that you missed a number, just like in
Oh,
your
yeah.
counting.
Yeah. Oh yeah. Because I like edit these ones. Like I like shuffle them around. on my syntax. Right. So number 10, Jacinda stands in Dunedin Stadium and looks at the crowds of people in the stands. Assume the illumination is sunlight with a wavelength of 550 nanometers. So wavelength is 550 times 10 to the negative 9 meters. Okay. And the diameter of the pupil. So diameter is equal to 4 millimeters again. So 4 times 10 to the negative 3 meters. And you want to find out the smallest separation between features on a face. That is, you want to find out the distance between, let's say, the eyes. So y is equal to question mark. And that person is 75 meters away. So this is x. Okay. Alright, so again we want y, so y is equal to 1.22 times the wavelength times x divided by d, so 1.22 times 550 times 10 to the negative 9 times 75 divided by 4 times 10 to the negative 3. That will give you 0.013 meters. So that's 1.3 centimeters.
So are these, sorry, you know how this is like an advanced tutorial, are these the hardest types of these questions that we get in the exam?
Yeah.
Wow.
So it's not that hard.
Yeah, because they basically give you everything that you need to just put into the formula.
Yeah, yeah.
So I can see your tricks and everything.
Yeah. It's just recognizing which ones are which. And that's why I use, because normally in the physics, like they say like this is S and this is R. But I found it like confusing. But I found it easier to remember if I just do Y and X, because then if I draw it like this, then I know that this is the Y value.
Oh,
And how
okay.
this is the distance between them
Yeah.
is X. Yeah.
Y to the sky. That's hard to remember it.
Yeah.
X across.
That one really stuck in my head. I don't know why.
But X is a cross.
So number 11, a student attaches 2 small bright lights, which are 10 centimeters apart, to the bottom of a helium-filled balloon. So really this should be going vertical, but normally I just draw it like this. So here's the lights, and they are 10 centimeters apart, so that's y. So y is equal to 0.1 meters. Okay, and then so it's traveling vertically upwards, so it's traveling away from you, and you want to find out the highest altitude at which you could still resolve the lights. So that's how far it will be away from you. So that's x. So x is equal to question mark, and you have your pupils here. So that's the pupil of your eyes, which is so that diameter is equal to 3 times 10 to the negative 3 meters, or 3 millimeters. And the wavelength is 550 nanometers again. So this time we want to find out x. So y is over x is equal to 1.22 times the wavelength over d. Okay, so we want to get x on its own. So you're going to flip the equation. So it's going to become x over y is equal to d over 1.22 times the wavelength. And then you can just move this one, multiply both sides by y. So this will come up here. And this can disappear on this side. Okay. So d is 3 times 10 to the negative 3. Y is going to be 0.1 and 1.22 times 550 times 10 to the negative 9, and that will be 447 meters. Okay. The last one. So this time we have a space station which is 400 kilometers altitude. So the distance is going to be x, which is 400 times 10 to the 3 meters, and it's 109 meters wide. So what's the minimum mirror size needed for a ground-based telescope to resolve 2 very bright lights, one on either side of the station? So this one's, if I saw this one at first, you might be like, oh, not really sure which one to use because it doesn't mention anything about circular apertures or anything. But if you have if they talk about resolving lights, that's going to be the circular aperture equation. Okay. So the bright lights are on either side of the station, which is 109 meters wide. So here's your lights, and they're 109 meters apart, so that's y is equal to 109 meters. Okay, and you want to find out what this diameter has to be. So y over x is equal to 1.22 times the wavelength over d. Okay, so you can just swap all of this with this one. Okay, so it's just going to be d is equal to 1.22 times the wavelength over y divided by x. Okay, 1.22 times the wavelength, which is 400 nanometers, so 400 times 10 to the negative 9 divided by y, which is 109, divided by x, which is 400 times 10 to the 3, and that would be 1.8 times 10 to the negative 3 meters, which has to be in centimeters, so just divide that by 10 to the negative 2, which will give you 0.18 centimeters. Okay? So yeah, it's not too bad. The glasses one can be a bit hard. Apart from that, optics isn't too bad as long as you understand the rules and you're familiar with what all the variables mean. So next week we'll start on radiation. Now radiation can be quite scary, but there's like just a few things that you need to know, and if you understand how to do the questions, then it's not so scary. And we'll go through all of those, all the types of questions that will come up. Okay? Alright. Cheers guys.
Thank you.
Thank you.